Welcome to Part 2 of the Deposition Processes for Microsystems presented by the Southwest Center for Microsystems Education. In Deposition Processes Part 1, we define deposition and discuss the importance of deposition in the fabrication of microsystems. We briefly talked about spin-on deposition and thermal oxidation. In Part 2, we will cover CVD, or chemical vapor deposition, physical vapor deposition, and electrodeposition. So let's take a look at each of these processes. The most widely used deposition process is chemical vapor deposition, or CVD. CVD is used to deposit thin films such as silicon nitride, polysilicon, zinc oxide, and silicon dioxide. In CVD, films are deposited as a result of chemical reactions between specific reactive gases or between reactive gases and the atoms on the substrate surface. The reactive gases are called the process reactants. The reactants are determined by the type of layer that you want deposited. For example, one type of CVD process uses dichlorosilane and ammonia for silicon nitride films. As you'll see in a minute, there are several different types of CVD processes. However, regardless of the process, CVD consists of three subsystems: a gas delivery system that delivers specific gases or mixture of gases to the chamber at specific flow rates, a gas removal system, which is a vacuum or exhaust, and a heat source. Here is a picture of a low-pressure CVD system, or LPCVD. This system uses a vacuum system to bring the chamber pressure down to a low process pressure and to maintain that pressure throughout the process. LPCVD processing is used when both sides of the wafers need to be coated with the desired thin film, and also for phosphosilicate glass, PSG, phosphorus-doped polysilicon, and silicon nitride. The primary difference between CVD systems are the amount of pressure required in the reaction chamber and the energy source. Atmospheric pressure chemical vapor deposition, or APCVD systems, use atmospheric pressure or 1 atmosphere in the reaction chamber. Low-pressure CVD, or LPCVD, uses a vacuum to reduce the pressure inside the reaction chamber to a pressure less than 1 atmosphere. Plasma-enhanced CVD, or PECVD, also uses low-pressure chambers, but a plasma is used to provide higher deposition rates at lower temperatures than an LPCVD system. This picture shows a glow discharge of a PECVD process. PECVD is used for films or wafers that contain layers of films that cannot withstand the high temperatures of the LPCVD systems. High-density PECVD uses a magnetic field to increase the density of the plasma, thus further increasing the rate of deposition. LPCVD and PECVD are the two processes commonly used for microsystems fabrication. When a micro device calls for a metal layer, the process changes from a chemical vapor deposition to a physical vapor deposition. Physical vapor deposition, or PVD, includes deposition processes in which the desired film material is released from a source as a vapor and then physically deposited onto the substrate. This deposition method is strictly physical. No chemical reaction occurs at the substrate as with CVD. It is analogous to water vapor condensing on a window. However, in PVD, once the vapor condenses, it forms a solid layer of material. There are two types of PVD processes that we'll review. One is sputtering, the other is evaporation. In PVD sputtering, molecules are dislodged or ejected from a source material or metal target by a high-energy particle bombardment. These ejected atoms or molecules travel to the substrate where they condense as a thin film. So how does this occur? The substrate, silicon wafer, and the film material indicated here as the metal target are both placed in the process chamber, and the chamber is brought down into the high vacuum region. An inert gas such as argon is introduced into the chamber, and a plasma is struck. This plasma is struck using an RF energy source. In the plasma, high-energy collisions cause some of the argon molecules to lose an electron, forming positive ions, shown here in the green circles. These ions then accelerate toward the negatively charged target, where they hit the target with enough energy to release some of the target material, basically vaporizing the target. The sputtered atoms from the metal target are shown in the gray circles. The sputtered target molecules travel away from the metal target and land on all the surfaces of the chamber and anything inside the chamber, including the silicon substrate. The high vacuum minimizes particle collisions as the vapor molecules from the metal target move through the chamber. Once the surface is reached, the vapor condenses, forming a solid thin film, as you can see here on the silicon wafer in dark gray. The other PVD process is evaporation. In evaporation, the metal source material is vaporized using a high-energy source such as an E-beam or high current. As in sputtering, a high vacuum environment is used to minimize the collision of particles as the vapor expands. Once the vapor expands to a surface, such as the substrate, it condenses, forming a thin film of metal. Multiple wafers are placed in the chamber using a planetary system, such as the one shown in this picture. During the process, the whole unit rotates for improved uniformity of the applied thin film. So looking at the evaporation process itself, here we see a vacuum chamber connected to a high vacuum system. For this system, the metal source material is a component of an electronic circuit. Since it is a metal, it has a low resistance. To start the process, the wafers are loaded into the process chamber, and the vacuum system evacuates the chamber into the high vacuum range. The voltage of the voltage source is then increased to supply enough current through the metal source to bring it to its boiling point. At this point, it begins to vaporize. The metal vapor expands to fill the chamber. The high vacuum minimizes the number of collisions that the vapor molecules may encounter, allowing them to reach the solid surfaces of the chamber as well as the substrates themselves. When the molecules of the vapor land on a surface such as these substrates, they condense, forming a thin film of metal. This process continues until the desired thickness is reached. Last but not least is electrodeposition, also known as electroplating. This process has been around since the 1830s, when it was used to copper plate printing press plates. Sunglasses, faucets, tools, jewelry, and other items that you are familiar with are coated with films such as chrome, aluminum, and even gold using an electroplating process. In Microsystems, this process is used to deposit films in the micro range. In addition to thin films, this process is also used by the Liga micromachining process to fill micro-sized high aspect ratio cavities with metal. This process itself is very simple. An electrolyte solution is made that contains metal ions of the desired metal film. An anode made of the metal to be deposited is immersed in the electrolyte solution and then connected to the positive terminal of a DC voltage source. A cathode, which is the object to be plated, or which holds the object to be plated, is also immersed within the electrolyte solution. The cathode is connected to the negative side of the voltage source. Once connected, the metal ions within the electrolyte are attracted to the cathode, where they are neutralized and begin to form a metal film on the cathode. As the metal ions are neutralized, additional ions are introduced into the electrolyte from the anode. This process continues until the desired thickness of thin film is reached. Let's briefly summarize this deposition overview. Deposition is any process that deposits a thin film of material onto an object or substrate. Thin film thicknesses can range from greater than 100 micrometers to only a few nanometers. Microsystems technology uses a variety of deposition processes, the most common being spin-on deposition, thermal oxidation, chemical vapor deposition, physical vapor deposition, and electroplating. The type of process used depends on the thin film being deposited and the desired thickness. For more detailed information on these deposition processes, be sure to download the Deposition Overview Learning Module from the SCME website under Educational Materials. Thank you for viewing this presentation produced by the Southwest Center for Microsystems Education.